For most users, local networks and the internet feel like an invisible utility. You connect to Wi-Fi and data appears, feeling almost like magic. But digital communication is a rigorously physical engineering discipline. Every email, streaming video, and database query is pushed through tangible, precisely configured hardware. To understand how this works, we have to look at the sheer industrial scale of the physical infrastructure required to keep modern digital systems running. This massive scale introduces a severe structural problem. IT engineers must design systems that can link thousands of endpoints while guaranteeing wire-speed data transfer and zero downtime. You cannot manage that volume of traffic organically. The only way to survive this scale is by separating functions through a highly strict modular design. This diagram outlines the solution, the hierarchical modular network design. It breaks the entire network down into three distinct layers: core, distribution, and access. Knowing how to navigate this architectural map and knowing which hardware belongs in which layer is exactly what separates a basic help desk technician from a professional network engineer. Before examining a single building's infrastructure, we must establish the highest level of network topology. This table breaks down network types by scale. At the very top of this scale is the Wide Area Network, or WAN. These are massive communication links spanning across distinct geographic locations, like entire countries or continents. The internet itself is a WAN. Stepping down one level of geography, we have Metropolitan Area Networks, or MANs. These are larger than a local network, but smaller than a WAN, explicitly designed to link infrastructure within a specific city limit or sprawling corporate campus. These vast geographic networks do not generate their own resources. They act as transit systems, routing traffic back to a highly secure, centralized hub. That hub is the data center, a dedicated facility engineered entirely for provisioning server resources and storing data in massive volumes. Because a data center concentrates so much computing power in one location, it requires specialized physical engineering. This includes dedicated climate control, robust power redundancy, and strictly enforced physical access control. These fortified sites act as the physical backbone for all cloud computing and heavy enterprise services. Without data centers, the geographic spans of MANs and WANs would be useless. They would have no centralized computing power to distribute to the endpoints. Now we drop out of the geographic span and step inside a single enterprise location to see how it manages local traffic. We return to our three-tier pyramid. This diagram maps the exact internal traffic flow for the local area network. At the peak is the core layer. Its primary function is wire speed data transfer. The core has a singular mandate: move data as fast as physically possible. To maintain that speed, it acts strictly as a high-speed backbone. It does not get bogged down by complex routing logic or granular security filtering. Beneath the core is the distribution layer, which handles the heavy lifting. It aggregates all the traffic coming up from the individual users, applies network policies, and actively routes that traffic to the correct remote resources. Finally, we reach the base of the pyramid, the access layer. This is the exact physical point where end users, their computers, and their individual devices actually plug into the broader network. Isolating these operations into three distinct tiers gives network engineers total control. If a switch fails at the access layer, it can be troubleshot and replaced independently without bringing down the enterprise backbone. Let's zoom in entirely on that access layer and examine the actual hardware operating at the edge of the network. The primary physical appliance here is the network switch. Its job is to provide physical ports for devices to connect to the local network. In a small home setup, you will typically find an unmanaged switch. These are simple, inexpensive appliances designed for very basic connectivity. Unmanaged switches are plug and play. They automatically forward traffic based on physical MAC addresses, but they offer zero configuration capabilities. You cannot adjust their settings. An enterprise environment demands rigorous control, which requires a managed switch. While the unmanaged switch blindly passes incoming data, the managed switch actively inspects, filters, and secures data frames based on specific programmed rules. This allows engineers to apply advanced security settings, configure virtual networks, and actively manage traffic loads across 24 or 48 distinct ports simultaneously. Modern access switches also provide a critical secondary feature: power over Ethernet, or PoE. This sends electrical power over the exact same copper cable that carries the data. Different devices require different power standards. The 802.3 AT standard, known as Type 2, delivers up to 25 watts, perfect for a desktop VoIP phone. But heavy mechanical devices, like a motorized pan-tilt-zoom security camera, require the 802.3 BT standard, which can push up to 100 watts over the line. The managed access switch operates as the crucial gatekeeper for the entire building. It provisions both secure data routing and physical electrical power to the absolute edge of the network. Looking behind those switches, we find the physical cables that physically link this entire architecture together. In an enterprise building, thousands of cables run through the walls. These runs terminate centrally at hardware frames called patch panels. The patch panel takes all that in-wall cabling and permanently organizes and labels it. From there, short patch cords are used to bridge the connection from the static panel into the active ports on the network switch. This slide outlines the foundational engineering rulebook for wired cabling, the IEEE 802.3 Ethernet standards. Modern networks rely heavily on the high-speed protocols listed here. 802.3ab defines gigabit Ethernet, while 802.3an scales that up to 10 gigabit Ethernet. To carry that speed, engineers choose between two main categories of physical cable: copper and fiber optics. Fiber optic cables transmit data using pulses of light. Because they do not use electricity, they are completely immune to electromagnetic interference. This allows them to support massive data speeds over extremely long distances, making them the standard choice for the core layer and WAN backbones. Down at the access layer, standard unshielded twisted pair copper cabling, or UTP, is usually sufficient. However, if that cable runs through a high interference environment, engineers must deploy shielded twisted pair. STP features an internal foil layer specifically engineered to block external electromagnetic waves from disrupting the copper signal. Choosing the wrong physical cable standard will instantly bottleneck your performance. A multi-million-dollar data center means nothing if the data gets choked out by the wrong copper wire at the access tier. If we follow that copper cable away from the patch panel, we finally reach its destination, the individual user's computer. Inside that computer sits the Network Interface Card, or NIC. This is the absolute physical terminus of the enterprise network. The NIC provides the physical hardware port for the cable to plug into, and its controller chip handles the raw data link layer communication, allowing the computer to talk to the local switch. Every single NIC manufactured in the world has a permanently assigned MAC address. The first half of that address is the Organizationally Unique Identifier, or OUI, which is assigned by the IEEE to specifically identify the hardware vendor. That MAC address allows the access switch to route data to the NIC over copper. The access switch hands that data up to the distribution layer, which aggregates it and passes it to the high-speed fiber core. The core pushes it out across the wide area network, where it eventually arrives at a fortified data center. A network is never a singular, magical entity. It is a precise, physically linked chain of highly specific hardware modules, each performing an isolated role. Mastering this physical topology, understanding exactly how an OUI on a microchip communicates through an access switch and up to a core router, is the professional baseline of IT infrastructure.